In our recent video, we talked a little bit about what the different greenhouse gases were and their different global warming potentials. So let's go a little bit into more detail about some of this radiative forcing. When we talk about this radiative forcing, we're talking about this overall a net positive or a net negative effect on warming in the climate. And we can see some of our summary figures. There's one in the book. Here's another one. This one is on the EPA website, and it's looking at the change in the effect of each of the gases over time in terms of how much they contribute to the overall greenhouse gas forcing component. So the graph here shows from about 1980 up to 2015, and overall you can see two interesting things. Of course, one of them is that the carbon dioxide is the green panel here at the top, which is the most significant warming influence, and this is mainly because carbon dioxide is the most abundant of these gases. And then the next highest contributor is methane. So these two gases, of course, we already are aware of. The other ones are all fairly constant, and that's one of the interesting things, that if you look at those CFCs and nitrous oxide, you can see a little bit of increase in the nitrous oxide since 1990, but the other greenhouse gases, at least the CFC 12 and 11, have stayed fairly consistent, which is good because we haven't been producing more CFCs since 1980 something, really. At least in the US, it's been phased out. And but we do have some other small contributors you can see that are kind of edging up down at the bottom. However, the trend in terms of the amount of forcing has shifted. And so this is another thing, right? We're paying attention to the total quantity, and we are also paying attention to the trends that are here. And so we can see a continuous increasing in the total amount of forcing that is happening, which tracks with our understanding that we are seeing a consistent increase in all of these gases, which we already talked about. So each of these gases has its own global warming potential, GWP, that we've talked about a little bit. And this does actually have a fairly detailed equation for calculating it. And although we aren't going to actually calculate it ourselves here, we are going to discuss it a little bit. So this, like other equations we've seen, this is an integral because it is the sum of a whole bunch of effects. And so this first term here, this is the greenhouse gas in question. That's what the GHG is for. And we've got sigma, and this is how well the gas, the greenhouse gas, GHG, absorbs infrared energy from the sun. So this is that first term. How well does it absorb it? And then we need to know how much infrared are we actually having reflected from the Earth? And then there's a time factor in here. And this time factor is a decreasing exponential. And it's for whatever time region we have. And so this is to reflect the lifetime of the gas. And then we have a unit conversion term at the end because we're scaling it for the molecular weight of whatever the gas is. And they don't explain where the 1,000 comes in, but they say it's a unit conversion, so I'll believe them. Anyway, the greenhouse warming potential is always scaled compared to the carbon dioxide, and so that's what's going on in the denominator, is that we've got this same stuff in the denominator, but it is for carbon dioxide instead of some other greenhouse gas. I missed the dt. So this looks like a complicated equation, but it's really not that different from how we calculated the photolysis constant, Kp. Remember, we had an integral there. We had a sigma, we had an f, and then we had the phi term. And we do have some additional terms in here, but this really is not all that different from that same kind of calculation. So this f, to go into a little bit more detail, this is the flux of infrared radiation that's heading out to space, and so might be absorbed. And then we already said that the sigma is how well the gas is absorbing infrared in general. The time exponential term there is comparing the lifetime of the gas to that of the carbon dioxide. And of course, we would need calculus in order to solve this exactly, so we are not going to do that. So we're going to leave radiative forcing as a topic to just generally be understood. These are the factors that are considered, and that we'll deal with them as we have to. And I wanted to talk about some other pieces of information here, because one of the things that you'll see a lot in conversations about climate change is you will see information that clearly, information about the climate that clearly happens from before we actually have any kind of written records. For example, if we switch on over here, this is back at the climate.gov website. And you'll see these graphs where they talk about the amount of carbon dioxide 800,000 years before the present time. And obviously we have not had analytical instruments even a fraction of that period of time, or people around to measure it. And we talked a little bit about using ice cores, and so I wanted to spend a bit more time talking about proxy data in general. So let's go ahead and have that as a new subheading here. So we generally already understand that proxy data are data that we use when we can't actually, we don't actually have these analytical measurements available. When we find proxy data, there's a lot of different kinds of proxy data that we can look at. And one of the simplest ones that doesn't take us back very far, though, is historical data that we might get from things like people's personal journals or newspapers. They might talk about the weather. You have some farming records, and you'll also get like ship records. Ship logs. The captains used to keep pretty close track of what was going on in the weather. So this is one of the ways that we get at least near-term information. If we want to look further back, then we have to look at some other information. And so one of those is from corals. And of course, coral tells us a lot about the environment in general. But I'm going to talk about corals and actually ice cores, and these two I'm going to talk about together, because of course corals and ice cores, they have these totally different ways of being used as proxy data, but they're related to each other. And what we're looking at here are isotope ratios. So when you have corals growing, then you know that these are made from calcium carbonate. And the calcium carbonate, we're going to learn more about this, but the carbonate is dissolved in the water. And so this carbonate is even coming from dissolved carbon dioxide, right? And we also have water that's present, that's going to be contributing. And all of these guys do isotope exchange. Okay, so anytime you have elements and compounds together in a system, you're going to get some isotope exchange as things change partners. And so let's kind of talk about what our most common isotopes are. So for carbon, our carbon-12 is our most abundant isotope. And then we have some slightly heavier carbon-13, and then we have radioactive carbon-14 that gets actively used for radiocarbon dating, right? That's the one that they use. For oxygen, we have oxygen-16 as the most common, and then we have oxygen-17. I think there's an oxygen-18 that's also radioactive. But anyway, these are the main ones that we are looking at. And then hydrogen, our standard, these are our most common isotopes, is hydrogen-1, and then we also have hydrogen-2 is one of our possible isotopes. So if we're talking about water molecules, then water in ice cores or water that is contributing potentially to an oxygen and a carbonate, then we could have hydrogen-1, oxygen-16, hydrogen-1, which would be sort of normal light water. And then we could have slightly heavier water with an oxygen-17. We could also have a deuterium. We could have a 17 and a deuterium, although the odds are pretty low. And of course, we've got lots of different combinations of these. So the interesting thing about some of these isotopes is that if we think about the water cycle, we have liquid water, and then it evaporates, and then it forms clouds, and then it falls down, and then it runs down in a stream and joins whatever our big source of water is, and then it goes up and around it again, right? So that's our water cycle. So if we have heavier water, one of these oxygen-17s, for example, this is harder to evaporate. So if we have colder temperatures, then we're going to have less heavy water in our clouds, and we're going to have more heavy water in our rivers and streams and oceans. And consequently, if we're looking at ice cores here, so for a colder year for the ice cores, we're going to get less O17 in the snow and ice because it will be less likely to have evaporated and formed clouds and then fallen as snow or ice. So colder years are going to give us a smaller ratio of O17 in our ice cores, but a higher O17 ratio in our liquid water, which then would be found potentially in corals. And so we can get a pretty good sense. I mean, you can actually correlate these, right? So oxygen 17 to 16 ratios in ice cores and in coral track with temperature. And we can look at current levels of snow and ice, current layers of snow and ice, and the oxygen 16-17 ratio to generate that calibration curve. And the same thing is true about current growth for corals. And then we can look back in the historic record and find in our ice cores what those oxygen 16-17 ratios are in the ice cores and figure out what the global average temperature was for that, or if not the global, at least the local average temperature was for that snowing season for the ice cores that year. So that's one of our ways, or that's two different ways of looking at proxy data. So the other two proxy data types that we're going to look at is we're going to look at pollen And we're going to look at tree rings. So these are two separate correlations that we're going to get. Right, pollen is little and airborne, and it goes everywhere, as those of us with pollen allergies know. And so it gets deposited in sediments of lake beds. It can be fossilized. You can find it in ice cores. And what pollen tells us is what kinds of plants were growing and how many, how abundant, how good was the growing season. More pollen probably tracks with more plant growth. And finding out what kinds of plants are growing and how much vegetation helps us understand what the overall climate was like. This might not get us specific temperatures and specific carbon dioxide levels from looking at pollen, but it is going to get us an overall sense of, was this a really cold place? Was this a tropical place based on the types of plants that were growing? Tree rings, though, and these are, sort of, it seems like, gosh, this would be not a very long-term project, but some trees grow for thousands of years if you don't chop them down. And when we look at the thickness of the tree rings and the density, then, and also the isotopes, because you can do tree cores just like you don't have to chop them all the way down. You can just take a core out of a living tree without hurting it. So if we look at the thickness of the rings, the density of the rings, the isotopic composition of the elements that are present, then again, these are going to correlate with temperature. So if we think about the long-term, this is now, right? And we have records that go back to, I don't know, at least a couple hundred years. We'll say 1800, right? So these are actual data. And then we can go back further with our historical records, a little ways. And then we can go back further with our tree rings, and probably even more than that, right? Thousands of years instead of just hundreds of years. And then pollen and ice cores and stuff, and corals, because you can also look at fossilized corals, although you won't get the isotopic compositions. But these ones will get you information in terms of proxy data for hundreds of thousands of years, as you can see. So I wanted to make sure that we were all kind of up on what proxy data was like as another subcategory of this particular lecture. So when we talk about, we're talking about climate change, right? And we've been tracking different effects on climate change, and we can see pretty clearly that we have lots of evidence that this is caused by, or at least our current warming and change, is caused by human activity. And there's lots more evidence than what we have talked about in these brief lectures, but I've given you a lot of resources for where to find some of those pieces of information. And so if you are having a conversation with somebody about it, hopefully you feel a little bit more empowered to bring hard data to that conversation. And if you want additional sources and strategies for communicating climate science, the ACS Climate Toolkit has some great resources for you. So I realize that this kind of conversation can feel pretty depressing when we look at you know, the carbon dioxide levels, and they're up over 400 parts per million and things like that. We have to kind of balance it with thinking about action as well to try and help ourselves not feel so depressed. So I like to think about this as required action, and I know not everybody feels the same way about it, but let's go ahead and take it there. So what do we need to do if we want to limit climate change? So we need to do really two big things, right? We need to limit emissions of greenhouse gases. And I guess this has a subcategory of working to remediate. To lower the levels of the greenhouse gases. And remediation really has two main parts here. So, you know, we talk about planting trees as one of our big ones. And then our second one is usually a chemical solution, which is often called like scrubbing, chemical scrubbing of the atmosphere or of exhaust or whatever. And we'll talk more about both of these two in just a moment. The next thing that we need is alternate sources of energy that don't involve greenhouse gases. And these are usually called renewables. And our big options here are mainly solar and wind power. But I think we also need to have a conversation about nuclear power. And so I'm actually going to create a separate video on nuclear power because I find that people tend not to understand it very well, and there's a lot of misinformation about it. And so this is an important education point for us, is to make sure that we are not miseducated about it. So we'll talk more about that in a little while. So as far as limiting emissions of greenhouse gases and use of greenhouse gases, this is a pretty complicated issue because there's a lot of money that's tied up into it. So really, money is getting in the way. There are lots of people around the world who are really coming up with some great alternatives or great ways to limit greenhouse gases and work to remediate them. And also coming up with excellent sources of renewable energy. But we have a pretty big investment in a lot of the big economies of the world in keeping the status quo. And so this is going to be one of our big challenges. So it's not something that we can solve during the course of this class, but it is something that we, I think, are going to need to deal with. So since this is a chemistry class and not a politics class, we're going to talk about some more of the chemistry that's involved in here. So our first remediation option, I talked about planting trees. And I think there's a project out there that's like the 100 million trees project that talks about if we plant all these trees, then we'll be able to absorb a bunch of the carbon dioxide that is currently in the atmosphere. And this is probably a really, really smart idea. So if you do a little bit of looking and poking around, it looks like young trees absorb about 13 pounds of carbon dioxide, we'll just say it that way, per year, because we know that trees and all photosynthesis processes start with carbon dioxide and water, and they effectively make sugar, right? Glucose. I'll just say carbohydrates. And starches, and cellulose, and all those kinds of things. And then mature trees are using even more, about 48 pounds of carbon dioxide per year. And that sounds pretty small, but if we think about the total number of trees that are out there, the internet tells me that we have about 3 trillion trees. in the world. Give or take, right? Who's counting exactly? But we've got a lot of trees in the world. And so 3 trillion trees times 48 pounds per year adds up quite a bit. And we'll play around with some of these numbers in our homework. But how much carbon dioxide are we emitting? So I did a little poking around on the internet, and we've got some different numbers. I think I found one on the EPA website. If it can be trusted, we hope it can be, that says that we used about 6.6 billion tons, or we produced about 6.6 billion, oh, it was metric tons, I believe. Let's double check. I think that was 2018. Let's do a quick check. Yeah, so this is our US greenhouse gas emissions in 2018. And they say that our total emissions were about 6.7 million metric tons, or in other words, 6,677 million metric tons, or in other words, 6.7 billion metric tons of CO2 equivalent. So, yeah, close enough. In 2018, and this is just the US. So this is pretty significant, and you know, the US is one of the major energy users of the world, so this is probably a decent percentage of the global amount of CO2. I mean, not like half or anything like that, but we will have to look a little further to find out how much the whole world is producing, if it can be estimated. So this, of course, only gets at the carbon dioxide. It doesn't get at the methane. It doesn't get at any of the other greenhouse gases. And this is only one of our possible tools in our toolbox. So we'll do some stoichiometry calculations and see how much that looks like. But this is just one of our possible remediation strategies. And we need to not be limited by just one. You know, we didn't get into this climate mess overnight, and it's not going to be an overnight fix. So let's talk about chemical scrubbing. And I also want you to know that there is lots of research on this. Lots of active research on this, not just research in the past, but there's lots of active research on chemical scrubbing, and there are a number of different strategies. One of the main strategies is to use amines, like this one. So this is an example. We have carbon dioxide, then we mix it with a liquid-based amine. So this is what ethanolamine. And it forms an equilibrium. So you're sort of effectively dissolving the, here we'll put aqueous in here. This might be liquid actually, but these are going to have to be considered aqueous kinds of things. I'm not sure. I'll have to look it up. Excuse me. Anyway, so this is one of our major strategies. This has been out there for a long time. It's well understood. It's not super inexpensive to set up, but is one of the most straightforward ones that's out there. Another really straightforward one is based on hydroxide, so the strong base. And there are several different strategies. I'm going to write out the one using sodium hydroxide. So if you take sodium hydroxide and you expose it to air, or you bubble air through it, then the carbon dioxide is going to react with the sodium hydroxide, and it's going to make sodium carbonate, which is a somewhat soluble solid, or excuse me, material in water. And when you take the sodium carbonate then you can react it with some calcium hydroxide, another strong base. And this allows you to regenerate the sodium hydroxide so that you can use this again, because you can then precipitate out the carbonate here from the sodium. If you remember your solubility rules, calcium carbonate is much less soluble than sodium carbonate is. So calcium carbonate will readily form a solid here. And this is pretty efficient. This is about 94% efficient at collecting the carbon dioxide and turning it into calcium carbonate. This is also an exothermic reaction. We'll probably spend some time looking at the energies too in some of our homework. So this is great because we can regenerate our sodium hydroxide, and so I suppose we could consider it a catalyst in these pair of reactions. But this reaction doesn't stop here. So calcium carbonate is limestone, and you can just leave it as is. But if you want to sequester the carbon dioxide, or if you want to use it for things like green cleaning, supercritical CO2 is used as a sort of green cleaning agent. If you recollect it again, then you can heat the calcium carbonate. So I'll put a triangle here for heat. And that will decompose it into calcium oxide and carbon dioxide. And this is also used in the cement industries. They take the calcium carbonate and heat it and turn it into calcium oxide and use the calcium oxide, but they don't usually collect the carbon dioxide. So then the calcium oxide can be reacted with the water, or with some more water, to regenerate that calcium hydroxide. So as long as you are capturing the carbon dioxide here, then this is a reasonable way of scrubbing carbon dioxide out of air. The problem is, what do you do with it after you capture it? You know, do you put it in compressed air tanks and then store it somewhere? I mean, this is not a long-term solution. So I would argue that stopping here is probably a more efficient way of sequestering carbon dioxide. Plus, it doesn't use the heat that's involved right here. So, you know, this is one of our possible strategies. So there are a bunch of other strategies that I'm not going to go through. If you are interested, then I would recommend that you just kind of start with a Wikipedia article on carbon dioxide scrubbing. They have a nice summary of it, and it talks about a bunch of other topics that you can take a look at. Or you can just go over to SciFinder or Google Scholar and look up some journal articles on it too. And you'll see that there's active research happening in this area. So this is where I want to kind of stop talking about remediation for a minute here, because I want us to have a sense of hope. You know, it can feel pretty intimidating to talk about climate change. I know yesterday when I was generating some of the videos, I was feeling super depressed. So I don't want you to feel that way. I want you to be aware that scientists are actively working on this, and we are finding lots of creative strategies to make sure that we can make this happen. And so what we need as partners are, we need citizens and governmental agencies that are willing to commit to also making the changes that you know, that we are finding in terms of these solutions. So in the next video, I am going to talk a little tiny bit about renewable power and just kind of generally talk a little bit about solar panels and wind and efficiency of those two, but also talk about how the generators work for those, just because it's not something everybody knows. And then I'm also going to talk, about how nuclear power works, because it's a pretty cool process and it's really important for us to understand. So look for our next homework assignment to be posted up on Moodle pretty soon.